Hello, my dear students, and welcome back. I know, exams are just around the corner, and the tension is probably building up. But hey, I'm here, so you don't have to fear. Together, we're going to make this chapter feel like the easiest thing you've ever studied. That's right, absolutely no tension. Trust me on this one. In just the next few minutes, we're going to get this whole chapter sorted out. It'll be crystal clear. So, what's our game plan? First up, we'll figure out what heat really is. Then, we'll see why things get bigger and smaller with temperature. After that, we'll look at a really magical trick that water does. Then, the big one, changing states. We'll also see how heat travels, and we'll finish with a very important question. How does your chai get cold? Ready? Let's begin. Okay, first things first. What's the deal with temperature and heat? Are they the same thing? Nope. You see, temperature is just, a number that tells you how hot or cold something is. But heat is the actual energy that's on the move because of that temperature difference. So just remember this one simple rule. Heat is energy in transit, and it always flows from something hot to something cold, never the other way around. Think about a hot cup of chai sitting on your table. It cools down, right? That's because the heat is flowing out of your hot chai and into the cooler air in the room. Simple as that. All right, now that we know heat is this moving energy, let's see what that energy actually does to things. This brings us to thermal expansion, and I've got a question for you. Seriously, have you ever noticed this? Next time you're on a train, look out the window at the tracks. You'll see these tiny little gaps. They aren't a mistake or bad construction. They're there on purpose, and physics is the reason why. And here is that reason. It's called thermal expansion. Basically, when most things get hot, they get bigger, they expand. So under our hot Indian sun, those metal railway tracks get longer. Those little gaps give them space to expand safely without bending or buckling. Then at night, when it cools down, they shrink back. Cool, right? Now, this expansion can happen in three ways. If you have a long, thin thing like a rod, its length increases. We call that linear expansion. If you have a flat sheet, its whole surface area gets bigger. That's area expansion. And if you have a solid cube or a ball, the whole thing puffs up. That's volume expansion. Okay, exam alert. This is super important, so listen up. For most materials, there's a really simple connection between these types of expansion. The volume expansion is roughly 3 times the linear expansion. Examiners love to ask about this, so just remember this simple relation. It's an easy way to grab some marks. Let's see how this works in real life. Picture a blacksmith trying to put a tight iron rim onto a wooden cartwheel. He makes the rim just a little bit smaller than the wheel. So what does he do? He heats up the iron ring a lot. It expands and gets bigger. Now he can easily slip it onto the wooden wheel. And then, as the iron cools down, it shrinks and grips that wheel with a super tight force. A perfect fit? All thanks to physics. Now, we just said that most things expand when heated, but there's always one rebel in the group, and in the world of materials, that rebel is our dear friend water. It does something really strange, almost magical. Look very closely at this graph, Butchel. This is a big one. As you cool water down, it shrinks, it contracts, just like everything else. But then, at 4 degrees Celsius, something bizarre happens. If you cool it down even more, from 4 degrees to 0 degrees, it starts to expand again. It's totally weird. And what this means is that water is heaviest, or most dense, at exactly 4 degrees Celsius. So, who cares, right? Well, all the fish care. This strange behavior is literally a lifesaver. In very cold places, as a lake gets colder, the water at 4 degrees, which is the heaviest, sinks to the bottom. The colder water, which is less dense, stays at the top and eventually freezes. So you get a layer of ice on the surface, but underneath the water stays liquid, and all the fish and plants can survive the winter. Isn't that just amazing? All right, let's keep moving. Next up is another topic that you will definitely see on your exam, the change of state. Solid, liquid, gas, ice, water, steam. Let's look at the physics of what's really going on. So check out this graph. It shows what happens when you heat ice. Its temperature goes up, until it hits 0 degrees Celsius. And then something fascinating happens. The temperature just stops. It gets stuck at 0, even though you're still adding heat. It stays there until every last bit of ice has melted. See that flat line? The same thing happens again at 100 degrees when water starts boiling. So where is all that heat going? It's going into something we call latent heat. I like to call it chupahua heat or hidden heat. It's the energy that's used to do the hard work of breaking the bonds and actually changing the state, turning solid into liquid or liquid into gas. All that energy goes into the change, not into raising the temperature. And the formula is nice and simple. Q equals M times L. And just look at this number. To turn just 1 kilogram of water at 100 degrees into steam at 100 degrees, you need over 22 lakh joules of energy. That is a massive amount of hidden energy that gets packed into steam. And this brings us to a very, very serious point. This isn't just a textbook fact. This is a real-life safety warning. This huge amount of hidden energy is why a burn from steam is so much more dangerous than a burn from boiling water. When steam hits your skin, it releases all of that latent heat first, and then you've got the hot water. So please be careful in the kitchen beta. Okay, team, we know what heat is, we know what it does, but how does it get from place to place? Well, there are 3 main ways, and to make it easy to remember, I call them the 3 musketeers of heat transfer. One for all and all for one. So first up is conduction. This happens when things are touching directly. It's just like passing a note to the friend sitting right next to you. Then there's convection. This happens in liquids and gases. It's like your friend actually getting up and walking across the classroom to give the note to someone else. And finally, we have radiation. This travels in waves and doesn't need any medium at all. It's like folding that note into a paper airplane and just throwing it across the room. You see these all the time. That lovely, cool sea breeze you feel at the beach? That's convection in action. And for radiation, think about a hot, sunny day. Why do we feel cooler in white clothes? Because white reflects the sun's radiation. Black clothes absorb that radiation, which is why you feel so much hotter wearing them. And for our final topic, let's talk about something near and dear to all of our hearts, how our cup of chai or coffee gets cold. And yes, the great Sir Isaac Newton figured this out too. Okay, that sounds a bit complicated, but it's actually really simple. All Newton is saying is that the hotter something is compared to the room around it, the faster it will cool down. That's why your super hot chai cools down really quickly for the first few minutes, but then seems to take forever to cool down those last few degrees. Let's look at a quick example. A really hot pan cools down by 8 degrees in just 2 minutes. But later, when it's much cooler, how long does it take to cool by just 2 degrees? Well, because the temperature difference with the room is much smaller now, it's going to cool down much slower. The calculation shows it'll take about 42 seconds. The key takeaway is cooling isn't a steady process. It's fast at first, and then it slows down. And I'll leave you with a final little puzzle to think about. Your friend tells you that if you want your chai to stay hot for as long as possible, you should add the milk right at the beginning, not at the end. Are they right? Use what you just learned about Newton's law to figure it out. I'm not going to give you the answer. That's it for me. You are all brilliant and you are going to do amazing. All the very best for your exams.